So we're continuing now, and we remembered that the correlation is given by the symbol r. That r squared, remember, was the percent variance explained. Both correlation is going to be a number from -1 to 1 describing the nature of the relationship between two random variables. When you square that, you're going to get a number between 0 and 1, which is going to be r squared, and that is going to be the percent variance in the original data set that is explained by another variable. And we'll be seeing more about what that means in just a little bit. But just to kind of be clear about our notation here, we're going to use the symbol y at first for our random variable. And there's going to be a reason why we're choosing y and not, you're probably wondering why not x, but okay, we're going to start with y. Y is going to be our random variable, and it's going to have some variance. Each observation is going to be different than the one before. There'll be a sample variance within the sample that we took, and the actual physical phenomenon that we're studying has some variance within it. There's a parameter, the variance, that describes the nature of the variability of the observations. Now, let's think for a moment as to what would be the best way to visualize this. How are we going to depict the variance in a data set? And what I want you to first think about is, what if we just took a cluster of observations of this random variable y? Now, I'm going to make a series of diagrams here where we have taken 9 observations of y, and I'm just plotting them as like a handful of variables along a y-axis here. So like each of those observations, like observation 1 is a certain distance from this y-axis, observation 2 is a certain distance. We're just kind of making like a bar graph here, just sort of illustrating how each of the 9 times we observed y, we got a value. Well, if we took those 9 observations of y, they have the real physical process y has some mean that describes it. We just don't know what that mean is, but based on the 9 observations that we have, we can take the average of it, y bar, which I'm illustrating here. That is the average of those 9 observations of y that we just sort of have lined up like a little bar graph right there. So each of the observations is either above or below, or I suppose hypothetically exactly on y bar, the average, but in general they are some distance away. See how I drew that with little dashed lines here that illustrates each of the 9 observations I took of y was some distance away from y bar. So like we can have, say, y5 is some distance from y bar, and that distance is y5 minus y bar. Or we could have like observation 8 is a certain distance from y bar, y8 minus y bar. The right word for that was anomalies. Each of those 9 observations has an anomaly. The distance it is from the average of the sample. Just kind of hold on to that word anomaly for a little bit, because we're going to see a similar term in just a minute. So anyway, so for each of our 9 observations, let's make it more general. For each of our n observations, we have an anomaly that is y sub n, well, y sub I minus y bar. That is the anomaly, how far that observation of y is from y bar. And so we can actually compute the variance of this data set based on these anomalies. It's basically the sum of the squares of the anomalies, where we summed up from I equals 1 to I equals n of y I minus y bar, that little quantity squared. So you just take the square of each of the anomalies and add them up. Then in the case of variance, it's divided by n minus 1, but we get this sample variance. Remember, the sample variance, its symbol is s squared. Sigma squared is the true variance, the parameter that describes the physical phenomenon. S squared is an estimator of that based on the sample of 9 variables, the 9 observations that we took. Okay, so we now know we have this random variable y. We have 9 observations or realizations of it, and they have some sample variance between them. Now what about if we had taken, at the same time we took those 9 observations of y, we also had 9 observations of x. We could like plot our values of x and y together on a scatter plot. And that's what I've done here, where I have made a scatter diagram where again I have my y-axis, but now I also have an x-axis. I still have the same 9 observations of y, but now, instead of just sort of being like a little bar graph type format, we're in a scatter diagram, where how far they are left to right on the diagram depends on the corresponding value of x of I. So like observation 8, which was pretty far down the y, it was a pretty big value of y, is also a pretty big value of x, so it's way far to the top right of the diagram. Observation 9 is a low value of y, and it happens to also be a low value of x. So it is way far to the bottom right, bottom left of our diagram right there. And so those same 9 observations now correspond, instead of being like 9 little bar graphs, 9 little bars on a bar graph, are now 9 points on a scatter diagram. And they're suggestive of the possibility, anyway, that there maybe is a relationship between this random variable y and this random variable x. I mean, it seems possible that we could maybe fit some kind of line into that cluster of data, that cloud of data that is the pairs of observations of x and y. Now, before we get any farther, let's pause for a moment and ask ourselves a question about that. Here's question 2. What did we call that line? That line that I just sort of have sketched in there? Back in Module 4 or whatever, when we started doing descriptive statistics, what did we call that line? Was it called the correlation line, the minimum variance line, the line of demarcation, or the best fit line? Make your choice from one of the 4 answers below this video, and we'll get some feedback before we move on in this lecture.